use this equation, this two-location equation, we should talk about what this means. So when we talk about a change in mechanical energy, a change in mechanical energy is when we take our mechanical energy at location 2 and we subtract it from our mechanical energy at location 1. Because delta means change. Change is final minus initial. So in a two-location problem, instead of calling it initial location and final location, I call it location 1 and location 2. And then I can go location 2 and location 3. If I want to, I can go location 1 and location 4. The idea is you can just keep adding. But when we talk about final, it's the ending one. It's the ending location. Okay, so that's how that change in mechanical energy means. It means my final mechanical energy minus my initial mechanical energy. And remember, when we talk about mechanical energy is this plus this plus this. So I have to talk about this plus this plus this at location 2, which would be in parentheses. And then we have to subtract my mechanical energy at location 1, which is this plus this plus this at location 1. And that also would be in parentheses. That's how we're going to deal with two-location problems. There's a special type of two-location problem, and that's the type of two-location problems we're going to start with. And that two-location problem is called a conservation of mechanical energy. And conservation of mechanical energy is a two-location problem, but it has like some conditions that need to be met. So in order for it to be a special type two-location problem, which we can refer to as conservation of mechanical energy, there's two conditions. If my work in is equal to 0, okay, and how is your work in 0? Well, there's no applied force over a distance, displacement. So if your work in is equal to 0, and your work done by friction is equal to 0, so there's no friction over some displacement, then we get a special type of two-location problem called conservation of mechanical energy. And the idea is if we take our work in and we take our work done by friction, and we can set that equal to ME2 minus ME1. But if my work in is 0, and if my work done by friction is equal to 0, we do a little bit of algebra, and I add ME to both sides. I get a special type of two-location problem called conservation of mechanical energy, which is ME1 is equal to ME2. And what this is really saying is all the mechanical energy an object has at location 1, all the kinetic and gravitational and potential elastic energy that that object has at a location is going to be equal to all the mechanical energy that that object has at a different location. Now we're talking about location 1 and location 2. But if there's no work in and no work done by friction, then it's really an infinite number of locations. It's any two locations that we pick. If work in is 0 and work done by friction is 0. Then ME1 equals ME2. We have to meet those parameters. If we don't, then it's not a conservation of mechanical energy, and we have to put in the work done by friction. We have to put in the work done by friction. We have to put in the work done by an object. Well, we're going to start with these special types. So let's take a look at the worksheet yesterday called in-class energy. So yesterday in class energy, I think we did problems 1, 2, 3, 4, 5. I think were the ones we did. We're going to skip number 6, and we're going to look at question number 7. So question number 7 says a 50 kilogram skier, we're on in-class energy worksheet, the worksheet called in-class energy. 50 kilogram skier starts at the top of a 100-meter high hill and skis down the hill. With what speed will the skier be going at the bottom of the hill if friction is neglected? So I think, in class problem number 7, I think a picture for these types of problems is helpful. So I have a hill with a skier, whether you want to draw a skier or not, completely up to you. Okay, there's my marvelous skier sitting at the top of my hill. Maybe don't need the skier, but the idea is that, okay? So we have a hill. When we draw these pictures, we're looking for stuff that we would use into those equations. There's a fair amount of equations, we just gotta know when to use them and when to cancel them. So some common things we want is we want mass, we want velocities, we want heights, we want spring stuff, we want applied forces, we want forces of friction, we want displacements. Now, if we ask any of those questions and the answer is 0, well then we don't actually need that number. But in the back of your mind, these are things you should be looking for, because those will help answer these questions. Now, the first thing we want to start off, and we say, hey, we start with a skier on top of the hill, and we're trying to figure out how fast, so that's a velocity, are they going at the bottom of the hill? The first thing to ask yourselves, is this a 1 location or a 2 location problem? 2, right? We're comparing the skier at the top of the hill, location 1, to the skier at the bottom of the hill, which I'm going to very strategically call location number 2. So what I'm really asking to solve for is I'm asking you to solve for what is our V2. What is the velocity of that skier at location 2, which we can simply refer to as V2. Couple things to keep in mind. We want mass. Mass is going to be a helpful thing. So it told us the mass of our skier is 50. I don't have to talk about the mass of the skier at the top of the hill versus the bottom of the hill, because okay, no, yeah, it's a 50 kilogram. Hi.
I was wondering if you guys had an iPad for Kenson?
I do not, no.
No.
I don't know if he left it at the back table.
Can I go check?
Sure, is he out in the hallway? Because he could come and check.
Yeah, Kenson.
He was at that back table by the door. That's where he was. But I don't have one otherwise. Yes?
Yes.
All right. That was very kind of you to come in and get it for me. So the skier's mass is 100, but they are the top of a 100-meter high hill. Okay, so the skier's mass on it. Now we don't have to talk about the mass of the skier at the top of the hill versus bottom of the hill, because unless they lose something going down the hill, their mass is going to be the same. Now it's possible. I've been skiing and see people lose stuff going down the hill, or fall and lose everything on the hill in their fall. But let's assume they don't fall in the process. So we start with 50 kilograms. In terms of things we're looking for work in, work done by friction, we're looking for heights, we're looking for velocities at the 2 locations. And spring stuff. I like to write my V1s, H1s, V2, H2s at my 2 locations. In my mind, that makes me very consciously think about, is there a velocity at that location? Is there a height at that location? Now, we will get to springs, so then in those situations we would include spring stuff, but there was no reference to any spring, so there's no spring stuff we need to worry about. Let's talk briefly about this 2 location problem. We said it was a 2 location problem, so because it's a 2 location problem, we need to use our 2 location problem equation. Work in plus work done by friction is equal to change in mechanical energy. Okay, So let's start with the work done by friction piece. The question that I have written on the board for work in, is there an applied force and a displacement? Does it talk about the skier being pushed by their friend? Does it talk about the skier using their poles to push themselves down the hill? Does it talk about them using the edges of their skis and doing a little bit of a skate before they go down the hill? It doesn't. So because of that, we are going to we're going to draw the conclusion that they're simply standing there and they're going to start to slide down the hill. So because there is no reference to being pushed, we can say that that work in is 0. We'll get to the point where we'll say, hey, you're going sledding, we're at George Street, snow day, your friend doesn't think you're going fast enough, and they give you a push for some distance. That's a work-in example. But it doesn't, that's not this. Is there work done by friction? Is there friction over some distance? Per the problem, what's it say about friction? It's neglected. Does that mean we have it or we don't have it? We don't have it. Now, how realistic is going skiing with 0 friction? Not very realistic. Okay, so the number we're about to calculate may be slightly skewed. But the idea is both of these are 0. So because both of these are 0, it's that special type of problem. It's conservation of mechanical energy, and we can say that ME1 is equal to ME2 because both of those values are 0. Okay? Because there is no work in, and because there is no work done by friction, it's that special 2 location problem called conservation of mechanical energy, where we can say ME1 is equal to ME2. Now let's look at location 1. What's V1, what's H1, what's V2, what's H2? We're filling in those values. So at the top of the hill, what's my V1? At the top of my hill, what's my H1? Now I probably should have drawn this in earlier, but I'm going to do it now. And it says that from the bottom of the hill to the top of the hill is 100 meters. That would have been something I should have drawn in my original picture. So what's my V1, or what's my H1? Let's start there. What's my H1?
100.
It's 100 meters. If my H1 is 100 meters, then my H2 needs to be 0. I've referenced the fact that height is relative. Okay? If we choose the bottom of the hill to have a height of 0, because that's where it was measured from, right? We measured from the bottom of the hill to the top of the hill. So if we choose the bottom of the hill to have a height of 0, then my H1 needs to be 100. But it doesn't have to be that way. You can define it however you want. If you wanted, you could define H1 to have a height of 0. You could say the top of the hill is 0. Perfectly fine. But if H1 is 0, then your H2 would have to be negative 100. Yeah, but it works out. Or maybe you say, well, I'm not at sea level. Sea level is, I don't know what it is in meters, but let's just pretend that my H2 was 500 meters. And if H2, if H2 is 500 meters, that's fine, but then my H3 or H1 would have to be, it'd have to be 100 more, right? It'd have to be 600. So it's up to you. You got to pick something to define it. Generally speaking, we choose the lowest point to have a height of 0, and we work accordingly from there. What about V1? What about V2? Well, V2, I already put a question mark there. That's what we're asked to solve for. That's our unknown. What about V1? Got to read kind of between the lines here. Yeah, 0, right? It doesn't talk about the skier moving. It doesn't talk about, it doesn't specifically give a velocity, so we got to kind of interpret that slightly. Okay, so now we have, if there was spring stuff, we'd include spring stuff. There's no springs mentioned here. ME1. ME is the combination of my potential elastic and my gravitational and my kinetic energy at location 1. So what ME1 is, and I really encourage you to expand this out, and say ME1 is equal to PEE1 plus PEG1 plus KE1. Those three things added together gives us ME1. And ME1 is equal to ME2, which ME2 is simply saying it's PEE2 plus PEG2 plus KE2. Mechanical energy is what we get when we add these three values together. So we expand out our conservation mechanical energy. I really encourage you to do that step. Because then we can go through and we can ask ourselves the questions that I had written on the board, and I very briefly went through again at the beginning of class. And we can ask ourselves those yes-no questions for these types of energy. And if the answer to that question is no, the value is 0, you can cancel that thing out. So for PEE1, we're talking about PEE is our spring. Is there a compressed spring at location number 1? To which you would say no, so we say that value is 0. For PEG1, the question we ask ourselves for PEG, is there a height? So since we're talking about PEG1, we say, is there a height at location 1? In which you would say, yeah, so we got to keep that one. For KE, the question is it moving? So is it moving at location number 1? In which you would say, no, right? We said that value is 0, so we can cross that thing off and that value is 0. Then we repeat the same questions, but now at location 2. So now we're looking at the bottom of the hill. And we can say, is there a compressed spring at the bottom of the hill? And you say,
No.
is there a height at the bottom of the hill? In which you would say,
No.
no. And is it moving at the bottom of the hill? And you would say,
Yes.
yeah, we just don't know how fast yet. But yes, it is moving. So our 6-variable equation simplified down to 2. Okay? Now this next piece, I can go through and say, well, PEG, we can calculate PEG by taking the mass of the object times our gravitational acceleration times the h. Now since I'm talking about PEG1, I'm going to talk about m times g times h1. Look, I already labeled h1. That's the value we're going to end up plugging in. And we got a 0 equals 0 plus 0. And our kinetic energy equation is 1/2 mv squared. But since we're talking about KE2, this needs to be V2. I never know how to approach this next step. I'm always kind of torn what to do here. Because I get students who are like, well, obviously, and then I get some students like, are you sure? So I'm always a little torn. But I'll introduce it and we'll kind of go as a class how we want to go with it. But if you look at that equation, the m times g times h1 is equal to 1/2 mv squared. Does that equation simplify at all? Can we reduce or can we simplify this equation? Do we have a variable that is in every single term on both sides of the equation that we can cancel out? We have a mass, right? We do have a mass in every single side of the equation. So we can cancel out the mass. This times 50, this 50 is going to be times 50 here, and it's going to be times 50 here. Overall, the effect that that has on my equation is none, because we're multiplying both sides by 50. We can actually cancel and reduce that. We can factor and simplify. And I don't know if we should, I don't know if we don't. Right now, it's pretty clear, and for a lot of these, we're pretty good with just canceling mass. But what happens eventually is when we have a PEE, if we look at our PEE equation, there isn't a mass. And if one term doesn't have that thing, we can't cancel it out. Okay, so because we have an M in every single term, we have an M and we have an M, we can cancel it. Do we want to cancel the M or do we want to keep the M?
Cancel.
Cancel, someone said cancel. If I want to keep it,
I would keep.
have a couple keeps. Okay, so it ultimately doesn't matter. It's going to change your numbers before the final product. If you're confident that you can cancel it, go ahead and cancel it. If you're unsure, we'll keep it. Okay? So let's keep it for the time being. So in this particular case, the mass is equal to 50. So I gotta take 50, and I multiply by our gravitational acceleration on Earth, 9.8, times the height at location 1,
49,000.
which is 100. And that's equal to 1/2 the mass of our skier, which is 50, times their velocity at the bottom of the hill squared.
Mr. Davis,
Yeah.
here in our assignments there is like 100 kgs, so we have to put 50 kgs instead of 100.
In class number 7?
Yeah, exactly.
Yeah, I just did.
We
No, you
have-
all got the wrong one.
You guys are looking at conservation one.
Yeah, I was looking at conservation.
Oh, we're looking at in-class energy.
Oh,
Boy, these
okay.
are they that similar?
Yeah.
10-meter hill, 100-meter hill,
Okay, I get it.
in-class energy, okay? Okay, so on the in-class energy, the conservation one, very similar apparently. Okay, so in the in-class one, it's a 50-kilogram skier with a height of 100. I think on the homework sheet, it's a 10-meter hill with a 100-kilogram skier. Very similar setup, slightly different numbers. Okay, so if we take 50 and we multiply by 9.8 and we multiply by 100, this left-hand side is going to be 49,000. If you would have chosen to cancel the masses, it would be 1/50th of what we started, but that's perfectly fine. So 1/2 times 50 times v squared is going to be 25v2 squared. Algebra tends to be the biggest mistake that people make when we set these up. So just be mindful of that and do everything you can to try to minimize your algebra mistakes. So it's 25v2 squared. So the next step to getting v2 squared by itself would be to get rid of that 25. So we want to divide both sides by 25. So then what that gives us is an answer of 1,960, which is equal to v2 squared. v2 squared. Now, since I have v2 by itself, I can take the square root of both sides, and our v2 is equal to 44.27 meters per second. Now, when you go to Granite Peak, and you go skiing, our hill here in this example is 100 meters, which about 300-ish feet, it's a little bit more, but about 300-ish feet. Granite Peak, I don't know, top to bottom, I think they claim it's right around 800 feet, something vertical. So this is less than halfway up Granite Peak. Now, this is a frictionless system, but this is basically saying if you were to go about halfway up the hill and you just go, you'd be going 44 meters per second, which a quick Google conversion is right around like 98 miles per hour. That's too fast. You should not go that fast on a pair of skis. You and I should not go that fast on a pair of skis. Okay? So, why do we not go that fast? One, hopefully we have a certain sense of self-preservation and we realize that that's not safe and we shouldn't do that. But two, is there's this kind of important thing called friction. which is really, really, really important because that's how we turn, and that's how we also don't go 98 miles per hour only going halfway down the hill. So friction is really a thing that we need to take into consideration. This is a model. It's this idea that if we had these conditions, then we can go through and we can talk about mechanical energy being conserved. So that's the only two location problem on that worksheet that doesn't have a spring on it. So I want to go through one more with you. Well, I want you to kind of go through this, and we'll kind of go, you kind of set it up, and we'll kind of go back and forth like that. So there's two problems on this sheet, very conveniently, or very creatively, I should say, called more in-class energy, because I didn't know what else to call it. So there's two problems on here, and we're only going to do one of them. So the problem that we're going to do is I'm going to ask you to do the second one. So the bottom one. Okay, so on the bottom of the worksheet called More In-Class Energy, it says a 50 kilogram skier is moving down the hill at 4 meters per second as they get off the chairlift at the top of a 40-meter high hill. How fast will they be moving when they crest the second hill that has a height of 50? When they crest as they go over the peak, the top of the second hill. That's what I'm saying. Assume that the hill is frictionless. So I started you off by drawing a picture. Take that picture, add some V's, add some H's, add some M's to it. Determine if there is work in, determine if there is work done by friction, and if the answer is there is no work in, and if there is no work done by friction, then it's a special type of two-location problem called conservation of mechanical energy. And hopefully by that point, we'll be talking already. So start by labeling your pictures, V1s, V2s, H1s, V1s, H1s, V2s, H2s, masses, spring stuff, and then start asking yourself some of those questions. Is work in equal to 0? Is work done by friction equal to 0? And then we'll probably be talking about it by that point. So start by labeling your picture. Oh, I guess probably the best spot to start is this a one location or two location problem? That's really where we should start. All right, let's start talking. One location or two location, I heard someone say it already, but this is a two location. And my two locations are at the top of the first and the top of the second. These are my two locations. That's a big step, right? Because we could, even though like the picture has this, we might actually be talking about right here at some point. Or we might start talking about here or here or here or here. And if it's a conservation of mechanical energy, it's any two locations are going to be equal to one another. There's an infinite number of locations that the mechanical energy would be conserved if it's a mechanical energy, a conservation of mechanical energy problem. Now let's start quick. Is my work in equal to 0? Does it talk about getting pushed or pushing off or anything like that? Okay, so work in is 0. Check. 1. Is my work done by friction equal to 0? How do we know that? Because it says frictionless. Check 2. Therefore, conservation of mechanical energy. Okay, so just kind of be thinking about that as we kind of move forward. So at the two locations, V's and H's and spring stuff would be great. Have they mentioned a spring in either location? No. So let's not worry about springs yet. Okay, we'll get to them next week. So V1, H1, V2, H2. So what's V1? At the top of the hill, V1 was 4. Okay, so they are not going 0 because they were riding the chairlift and they just got off the chairlift, which apparently dumps them straight down the hill. Okay? What's my what's my H1?
40.
Most people choose H1 to be 40. And the reason they tend to choose H1 to be 40 because it talks about that hill is 40 meters high. Okay, and that's great. It's pretty common. It's what I would do probably too. If H1 is 40, then my H2 is 15, right? Because we're measuring from this point, which we have defined to be 0. The lowest point is 0, and as long as we're consistent, we're fine. Some people like to say H2 is 0. And that's fine, but if H2 was 0, then my H1 is no longer 40, it's going to be 25. Right? Because we're saying if from here to here is 15, well then from here to here is the difference of 40 minus 15, so it's be 20. And some people like that because we get another 0, which is really kind of nice and convenient. And in this particular problem, once again, it's asking you to solve for how fast are they going at the bottom of the hill. This was a special type of mechanical energy, conservation mechanical energy, that said work done in plus the work done by friction is equal to the change in mechanical energy. And because this was 0 and this was 0, then we could say ME1 is equal to ME2. Now, if that's how far you've gotten already, great. Expand out, what does ME1 equal ME2 mean? What is ME1? What does that look like? PEE what? Plus what? Plus what? What is ME2? I'll give you about, I don't know, 20 seconds, and then I'll write it down for you. So that's what ME1 equals ME2 looks like in the fully expanded form. ME is the combination of PEE plus PEG plus KE. And at location 1, we add a 1 next to each one. Mechanical energy at location 2 is this plus this plus this. At location 2 is 2 and 2. Now let's ask ourselves the questions that go along with these energies. The question we ask ourselves for PEE is there a compressed spring? And at location 1, is there a compressed spring? No, so we can cancel that out. At location 1, is there PEG? The question we ask ourselves for PEG, is there a height? So is there a height at location 1?
Keep it.
Keep it. At location 1, is there KE? Is it moving at location 1?
Nope.
Yes.
Yes.
Yep, right 4. So we got to keep it. At location 2, is there a compressed spring? No. At location 2, is there a H2? Yeah. That's where some people like to say H2 is 0, just for the record, because then they can cross that one off. But then you got to redefine each one. That's fine. At location 2, is it moving? Yeah, we just don't know how fast yet. So we now have 4 different types of energies, 2 at each location, that we need to address. So my formula for PEG 1 is M times G times H 1. My KE1 is going to be, I have to add, my KE is 1/2 MV1 squared And that's equal to PEG2, which is M times G times H2, plus my KE2, plus 1/2 MV squared, but because we're talking about location 2, it has to be V2. Now, if I had an equation that said 2m x plus 3my is equal to 4mz, is there any variable that is in every single term on both sides of the equation? Yeah, and if the answer is yes, then we could factor out an m. And then because we have an m, we could divide both sides by m, and we can cancel out an m. Okay? If we have an every single term on both sides. However, if we had that, can I factor out an m? Can I cancel out an m? No, because I don't have an m in every single term on both sides. Now the reason I'm pointing this out is because of this. Can we cancel something out? I can cancel an m because I have an m in every single term on both sides of the equation. But if I had that, I can't cancel out an m. I need it to be in every single term on both sides. I do have an m in every single term on both sides. So this is again up to you whether we cancel that m or we don't. We didn't last time. Do we want to cancel it this time or should we leave it in? I really don't care. I heard one of each. I'll cancel it this time. Okay? So because I have a mass in every single term on both sides, we can cancel it out. Now, if you are in any question about whether you can or can't cancel it, keep it in. It will not lead you astray. I don't know if that was the right use of that phrase, but I don't think so either. But it's okay. Hopefully you won't get it wrong. Okay? When in doubt, leave it in. So if we chose to cancel it, which I'll do this time, we can say 9.8 times my h1, which is 40, plus 1/2 our v1, which was 4, and then we square the 4. And that's equal to 9.8 times 15 plus 1/2 v2 squared. If I remember what these numbers were, I think this is 392, I think this is 8, I think this is 147. I think. I'll verify that in a second. And 2, 8, 147. Okay. Now, again, algebra tends to be the thing that people screw up the most frequently. I combine like terms. This is a like term, this is a like term, this is a like term. That last one is not a like term because there's a v2 of it. So I can't combine them. So I have to add this and this, that's 400. And then that equals this, so in order to get this to the other side, I'm going to subtract. So we're going to take 400 minus 147, which is 253. Okay, so now I would not suggest taking the square root yet. Algebra tends to get screwed up then. So before I take the square root of v2 squared, I need to get rid of this 1/2. There's two ways you can get rid of a 1/2. You can multiply by the reciprocal, multiply by 2, or you can divide by 1/2. you can divide both sides by 0.5. And either one is perfectly fine, and they'll give you the same value. And in this case, 506. Okay, we get 506 is equal to V2 squared. Now we can take the square root of both sides, and we get a V2 that is equal to 22.49 meters per second. Okay, on Monday, no, sorry, getting ahead of myself. Tomorrow, sorry about that. Tomorrow, I'll have you and we'll kind of bounce back and forth between going through that first one, and then I'll give you work time on that worksheet called conservation. I changed the due date. The original due date when I handed you that sheet yesterday was tomorrow, conservation one. It's already been pushed, it's already been changed, because I'll give you some time to work on it tomorrow, but we'll go through that one kind of back and forth, have you try it, and we'll just kind of verify that you got it right. Once that bell rings, which we're still about a minute and a half away, you're welcome to leave. If you have any questions, please let me know.